line defects, and you can see here dislocations. Okay, for dislocations, they are typical line defects. Dislocations, they are line defects, and they slip between crystal planes. Result when dislocation moves between crystal planes when the dislocation move and produce permanent plastic deformation. I want you to pay attention to this statement. Dislocations produces the permanent means plastic deformation. Here is this is a schematic of zinc, which has HCP crystal structure. This is before deformation. So here is after tensile. If we apply the tensile load on these two ends after tensile elongation, and we can see. So this is a bar, this is a specimen, and it stops this way. So this is a slip between crystal planes. This is a slip between crystal planes. So this is a dislocation. Linear defects, dislocations are the major type of linear defects. They are one-dimensional. Last time we showed you there is a line. These are one-dimensional defects around which atoms are misaligned. I'm going to show you the figure in next slide as well. And linear defects, we have dislocations. We have two different kinds of dislocations. And the first one is edge dislocation. Edge dislocation, extra half plane of atoms inserted in a crystal structure. And also, so this is the direction. This B is a Burger's vector B, B perpendicular to dislocation line. And the second one is a screw dislocation, the spiral planar ramp resulting from the shear deformation. And in this case, the Burger's vector is parallel to this dislocation line. I'm going to show you. And here, this edge dislocation. So here's edge load dislocation. This is the 1, 2, 3, 4, 5, 6. So these are 6 complete planes. However, if we put an extra half plane crystal plane as this one here in between this third one and the fourth one, and this we will have resultant crystal structure like this figure shows. From this one, okay, this one is called edge dislocation line, and so we use this sign to denote this edge dislocation line. And the B is a Burger's vector, is perpendicular and to this guy's orientation. This guy's orientation. So here is a motion of edge dislocation. Dislocation motion requires the bumping of a half plane of atoms and from left to the right, successive, and bumps across the slipping. The planes are broken and remade in succession. You should be very. I'm sorry. So this is admission does not work in this one. I'm going to email you the animation of the class. So here is atomic view of edge dislocation motion, and from the left to the right as the crystal is shear, if you apply the shear force. And then we talk about the second type of dislocation, which is called screw dislocation. And so here is our material, and you can see here. So this is dislocation line. Okay, so this is a dislocation line, and so in this direction, this is a Burger's vector. And if you have at the very beginning, and suppose this line is at this location, and so this line is at this location, but for some reason and you just shear it and just shear it, okay, and shear it and screw it, just like a screw it. And for this picture shows very clearly. And so, this line comes from this line to here, and the same thing for the C point. So here this location line, right? So this is a Burger's vector. So VSME, so this is screw dislocation. In VSME, if you have about the textbook, I just think you have these resources and to see and how it moves. You can see I just have applied the load, and you can have it moves screw this way. Excuse me. A region of crystal containing a dislocation can be rotate the screw in 3D, and dislocation motion may be animated. This is the front view and this is the top view. Edge screw and mixed dislocation. In practice, practically speaking, in reality, we do not only have edge dislocation in this case, or this screw dislocation in that case. On the contrary, and we usually have mixed dislocations. That means that we have both edge dislocation and a screw dislocation, and in almost all of these physical phenomena. So look at here, edge. Okay, so here it goes this way, right? So this is it goes here. You just screw and mix the dislocation. So this is edge, the edge moving here, right? This is edge. You can see here. This is the extra edge. I'm talking about the extra edge. So this is a screw, just a screw rotate. You just rotate. Just assume we have a center for this rotation, and just rotate it. And so this is the top portion and this lower portion, and they have relative motion. So this is mixed. You need to know that this is mixed. This is not just edge dislocation or screw dislocation, both. Then we talk about how can we identify these imperfections in solids. So these locations are visible in electron micrographs. You can look at here. So these is the dark lines. These are dark lines here, and they are these locations. And whenever in our quiz or exam, I might give you these electron micrographs, ask you what are these dark lines, and then you should be able to tell me this is dislocations. Then we talk about dislocations and the crystal structure. And this is structure, closed packed planes and these directions are preferred. Closed packed planes and directions are preferred. You can see here, view on two closely packed planes. Close packed planes. These are close packed planes and top HCP. Okay, so comparison among crystal structure. So FCC many close packed planes and directions. HCP only one plane and three directions. And BCC none. BCC none. So these are specimens that were tensile tested. Here. And then we talk about interfacial defects. Interfacial defects, as the name suggests, these are interfacial boundaries that have two dimensions and normally separate regions that have different crystal structures and or crystallographic orientation. So these include external surface. We know the external surface along which the crystal structure terminates, and the grain boundaries having different crystallographic orientation in polycrystalline materials, and face the boundaries and uh, exist. I'm sorry, this is a typo. Exist and in multi-phase materials, these phase boundaries, and also the twin boundaries. So this is commonly seen individual defects. As I said, I'm very interested in these basic concepts. So in our quiz or the exam, I might test your understanding of these basic concepts. You should be able to answer these questions and correctly. The green boundary, the most commonly seen, this is interfacial, the defects here. This is green boundary. You can see, okay, have this is one green, this is one green, and so this is one green, and you can look at here. So this green and this green, they have different orientation, and you can see here, okay. So this here and here. So these are two origin. This is lines here, and you can see this is a misalignment angle, and also here. So here is this is the direction for this grain. So here is the direction for this grain, and if we extend these two lines, we have this form angle. This is also called angle of misalignment, and you can see, as I said, so even though this is multiple grains, they have the same material, but these materials, they are aligned um, with different orientation, and then we have this result in this polycrystalline material. It means that this mechanical properties for this one is different from this and different from this also. So here is we call small angle grain boundary. This is small angle. This is a high angle the grain boundary. The grain boundary definitely is treated as interfacial defects. Then we talk about the planar defects in solids. One case is a twin boundary, and it's called a plane. So here is a twin plane. This is a twin plane, a core boundary, essentially a reflection of atom positions across the twin plane. So you can see why we call the twin. Twin is a mirror. This one is related to this one, this, and so on and so forth. The stacking faults, this is stacking faults. They do not go repeated this pattern, but they have a different pattern here. So this is called stacking faults. For FCC metals, an error in ABC packing sequence, for example, ABC, AB, A, and BC, this kind of stacking faults. Catalyst and surface defects. Catalyst, ever have you ever heard of the catalyst? The catalyst is called a material that can change the rate of a chemical reaction without being consumed. This should be changed, not increased here. So this is what I have learned is we call changed, not increased. But usually we use a catalyst and we want to increase the rate of chemical reaction. So here is the active sites on catalysts are normally surface defects. So here's a crevice, this is a ledge, terrace. So here is a kink, vacancy. This is a step. Here is, look at here. Okay, so this is a single crystal. This is Celsius zirconium dioxide used in automotive catalytic converter. As you can see here, they are called the surface, the defects. Uh, And then we talk about microscopic examination and crystallize the grains and these grain boundaries vary considerably in size. Be very careful, okay? And can be quite large. And for example, large single crystal of quartz and or diamond or silicon. Um, Aluminum light post or garbage can and see the individual grains. You can see the individual grains. Crystallized or the grains can be quite small, in millimeter or less, necessary to observe with a microscope. That means they can be very big, can be very small. First, we talk about optical microscopy. I do not know whether you have had the experience of using optical microscope. Um, Useful up to 2000 magnification. Polishing removes surface features, for example, scratches, etching changes reflectance depending on crystal orientation. So this microscope, so here is a polished and etched this surface. Crystallographical planes. So this is crystallographical planes. So here is what we see and using this as optical microscope. So this is what we see here. So microscope of brass. This is which is alloy, uh, copper and zinc. Optical obscope, microscope. You can see the green boundaries here. You can see green boundaries here. Green boundaries are imperfections, are more susceptible to etching, and may be reviewed as a darker line, and changing crystal orientation across boundary. And so here is the polished surface, this green boundary, and we can see this is grains, and these are grain, all these are grains. So we can see ASTM grain size number. These are number of grains per square inch, and they are n equals this is a grain size number. Okay, so the grain size number. ASTM. Do you know what ASTM is? ASTM is American Society of Testing and Material, and so this very important organization. They defined and many procedures that engineers need to follow. So I will talk about this one later. So here this gives us an equation how to calculate the number of grains per square inch. So this is grain size number lowercase n. Optical microscope, and we'll talk about the polarized light. Metallographic scopes often use polarized light to increase the contrast. Also used for transparent samples, such as polymers. Microscopy, optical resolution, and can be 10⁻⁷ meter, which equals 0.1 micrometer, which equals 100 nanometer. For higher resolution and need a higher frequency, can we use X-rays? So difficult to focus. We use electrons. Electrons is a better option. Electrons wavelengths, the 3 picometer, 3 picometer, pico is 10⁻12, nano is 10⁻9, femto is 10⁻15. You should know the relationship between these words. Magnification, so here is 1 million. Atomic resolution possible electron beam focused by magnetic lenses. And then we talk about scanning tunneling microscope. These atoms can be arranged and imaged. This is for this one. You can see this is like a cookie. Carbon monoxide molecules arranged on a platinum 111 surface. This is a platinum 111 surface. So here is very interesting. So here is the two characters. I do not know whether you know these two Chinese characters, because my origin I know, and this is 原子. 原子 in Chinese language it means atoms, and so people used this is STM to build the 原子, the atom in Chinese, for these iron atoms arranged on a copper 111 surface. So these are very full of art. It's very beautiful, artistic. Summary. And for these imperfections, we have talked about the point, line, and area defects exist in solids. The number and type of defects can be varied and controlled. For example, the temperature controls vacancy, concentration. Defects affect material properties. You should know that. Okay. For example, grain boundaries control crystal slips. And defects may be desirable or undesirable. It depends on what is your application. For example, dislocations may be good for or bad, depending on whether plastic deformation is desirable or not. Right? So this depends on your application. So whenever you do research, and think about this. How can I use my knowledge, use this physics, and to achieve my application goals? So this is called research.